When we talk about water as being a universal solvent, not only do we need to know that water is there, but we also need to know how much of the polar and ionic substances that dissolve in water is present. So this is what we call the concentration of the solution. In a solution, there is two components. There's the solvent, which in this case is water. When we're referring to aqueous solution, we're talking about a water solution where water is the solvent. And then we also have a solute. And solute is the substance that's dissolving. That could be table salt, which is a solid, could be sugar, which is solid. It could be a gas like carbon dioxide in your beverages. It could also be another liquid. For example, in wine, we have some ethanol or alcohol dissolved in water. So the solute could be anything. The solvent in this case is water. When you mix the two together, you get the solution. Now, when we have a solution, we give it a different symbol. Remember, we used to have solid, liquid, and gas with the letters S, L, and G representing their states, but now we have AQ representing a solution. So if I take table salt, which is NaCl, in a solid form and I mix it with liquid water, I get NaCl, but now in aqueous form. So AQ represents that this NaCl is mixed with water. In qualitative terms, there's two ways to look at concentration. We can say a solution is concentrated when we have a large number of solute that's dissolved in the solvent. We can say that the solution is dilute if there's only a small number of solute that's dissolved. And this is just a picture showing you if I were to dissolve something that has a reddish color, the more concentrated it is, the darker that red color will be. Vice versa, if it's dilute, it's going to be lighter. Now, there's actually quantitative measures of concentrations that we use in chemistry. I'm going to show you several of these. The first three you might recall when we discuss air pollution, we have looked at before, which is percent, parts per million, and parts per billion. In that context, we were also talking about solutions, except that we're not talking about aqueous solutions at that point. Air is a solution because you have a gas like oxygen, for example, mixed with larger quantities of other gas like nitrogen. So you can think of that whole mixture as a solution, and you can quantify how much oxygen is present in 100 parts of that solution, or 1,000,000 parts, or 1,000,000,000 parts, depending on which one of this unit you're using. We have something a little bit more unique here that is used a lot more with aqueous solution, which is the unit molarity. So molarity is defined as the number of moles of the solute that you have divided by the volume of the entire solution. Going back to this picture here, I would take the number of moles of the solute. Remember that if I know the mass, I can convert it to moles. And then I would divide that by the volume of this entire solution, this blue solution right here. When we say something is 1 molar with this uppercase M symbol, we mean that it has 1 mole of solute in 1 liter of a solution. All right, now we're going to take a look at a couple of problems here on calculating concentration of solute in a solution. The first problem here says you have 5 liter of a solution that contains 80 micrograms of mercury ion, and you're asked to express the mercury ion concentration in units of ppm and ppb, parts per million and parts per billion, and then you have to determine whether that complies with the regulations of having only 2 ppb for mercury. So let's check that out. So converting to ppm or ppb units is really just a matter of multiplying by the factor that you're looking for. So if you recall, when we try to convert something to percentage, let's say I have the number 0.22 and I'm trying to convert it to percentage, then what I would do is just take that number and multiply it by 100%. 100% is just 100 over 100. So anytime I want to convert it to some kind of a unit that is parts per whole, I multiply it by that number, but then as a factor of 1. So 100 over 100 is just equal to 1. So if I want to convert to parts per million, in this case, I need to multiply it by 1,000,000 over 1,000,000 to make sure that it's converted into that unit. Now, 1,000,000 over 1,000,000 again is 1, which is just 10 to the 6 over 10 to the 6. And that's what I'm going to do here. So first I take the 80 microgram divided by 5 liter. I want to convert that microgram to grams because the expression of these quantities is in grams. So you see that I did this conversion factor. Hopefully you recall how to do those metric prefix conversion from chapter 1. Once we do that calculation, 80 divided by 5, that gives me 16 over 10 to the 6. I'm leaving 16 over 10 to the 6 because I'm going to multiply them by 10 to the 6 over 10 to the 6. And the reason I want to leave that 10 to the 6, I could have divided this whole thing 16 by 10 to the 6 and just get a really tiny number and then later on multiply it by both of these, 10 to the 6 over 10 to the 6. I'll get exactly the same answer. So the reason I'm doing this way is because I can just cross cancel that 10 to the 6 and my answer would then end up being 16 ppm. Now, if you want to convert this to ppb, or parts per billion, all you need to do is just take that 16 ppm, which is again, that means 16 out of a million, and then multiply it by 10 to the 9th, which is a billion, over a billion. Now 10 to the 6 and 10 to the 9 will cancel out so that you're left with 10 to the 3rd at the top, which is 1,000. So then 16 times 1,000 is 16,000 out of a billion, so 16,000 parts per billion. Will this comply with regulations, which is 2 ppb? And the answer is absolutely not, right? Because we are so way above what is allowed for mercury in solution. Okay, the next question is about calculating molarity. Here it says, what's the molarity if you have 2.05 grams of sodium chloride dissolved in 582 milliliters of water? So the molarity definition is number of moles of solute over volume of solution. That means to get molarity, you're going to need two numbers. You're going to need the number of moles of the solute and you're going to need the volume of the solution. I want to remember that 1 molar is defined as 1 mole of the solute over 1 liter of a solution. That allows us to convert the numbers to the appropriate unit. So what you want to do first is just calculate the number of moles of the solute. In this case, the solute is sodium chloride. It's sodium chloride that's dissolved in water. And then you want to calculate the volume of solution in liter. And then lastly, you want to divide the two numbers to get your molarity. So the number of moles of sodium chloride is just the mass divided by the molar mass. We did this calculation in the prior chapter when we're converting from mass to moles, and you're going to get 0.0350 moles. Just to make sure people see this, the units do cancel out to give you moles. Now the volume of the solution, you're going to take the 582 milliliter, and you might say, those of you who are paying attention to details will see that this is 582 milliliters of water, and water is the solvent, not the solution. However, typically we put a small enough quantity of the solute that the amount of water is overwhelming, and then the addition of the solute doesn't really change the volume. So unless you're given some other information, you can assume that that 582 milliliters is also the 582 milliliter of the solution. All you need to do here is convert this to units of liter, and so that's what I'm doing in this calculation. I get the liter to milliliter conversion factor, which is 1 to 1,000, and I get 0.582 liter. And then the molarity would just be the division of those two numbers, the number of moles and the volume, and we end up getting 0.060 molar.